Hey everyone, in this video we are going to get a little introduction to something called trigonometric substitution. So the idea is going to be a little bit similar to what we did with u substitution, but it's a little bit more complicated because instead of using u, we're going to use a trig function. So let's start with a bit of motivation for what kind of integrals might require this new method. So this here is actually not such an example, but that's only because it is a definite integral here. So the fact that this is from 0 to 3 is actually quite important. So you may have seen this in Calc 1 or whenever you were first introduced to some integrals. So remember that since this is a definite integral, this is some notion of signed area. And this curve here, y equals the square root of 9 minus x squared, is the top semicircle of radius 3. So this is exactly what square root of 9 minus x squared is. And so if we're only looking from 0 to 3 for x, that would just be this right half of our semicircle, or a quarter circle. And so this integral, this definite integral, is the signed area of a quarter circle of radius 3. And because of that, we actually don't really need to use the fundamental theorem of calculus at all. We don't need to find an antiderivative or anything. We can just compute this using, pi r squared, but over 4 because it's a quarter circle. Our radius is 3, and so this is 9 pi over 4. Right? So I can just use geometry here. But the second that I change this to an indefinite integral, and I'm literally just asking for an antiderivative, I got some problems because now I can't use geometry anymore. I'm not really talking about an area here. I'm talking about an antiderivative. And additionally, I don't really know how to deal with this. This isn't a rational function. I can't use partial fractions. Not really a product of things, and it doesn't seem like integration by parts is the way to go. You might think, hey, I've got an inside function here. Could I use u substitution? But the problem is its derivative doesn't show up, right? There's no x on the outside. And so the fact that the derivative of 9 minus x squared is negative 2x, we don't have the right du piece here. And so u sub also won't work. And so this is actually an example of something where trigonometric substitution will work. So before we do that problem, I'm just going to do a quick little aside here. So this is something that I would always give you. Well, I guess specifically these two here. But these are some trig identities that are very useful for trig substitution in general. So this first one is the Pythagorean identity. It's one you may be familiar with. It's literally just coming from the Pythagorean theorem. So when you're on the unit circle, your x value is given by cosine of your angle theta. Your y value is given by sine of theta. And if you're on the unit circle, your hypotenuse is always 1. And so the Pythagorean theorem literally gives you sine squared plus cosine squared equals 1. The second thing here is also the Pythagorean identity, but you just divide through by cosine squared. So start with sine squared plus cosine squared is 1. If you just divide both sides by cosine squared, then that won't change anything, right? It won't change the fact that they are equal. And sine squared over cosine squared, sine over cosine is tangent, so that's just tangent squared. Cosine squared over cosine squared is 1. And 1 over cosine squared, well, 1 over cosine is secant, so this is secant squared. And that's where this comes from. So this is also Pythagorean identity, just in a different guise. The last two are not related to the Pythagorean theorem. These are what are called the half angle and double angle identities. There are actually several half angle and double angle formulas, but these are the two that kind of show up the most and are most useful. And so these are things that we will use in the problems ahead. Okay, so just keep those in mind. They will show up. They will make life a little bit easier. All right, so now back to the integral that we were talking about. So at first, I'm just going to give you the substitution and not really explain why. And then after we finish this problem, I'll explain how to know when to use trig sub and also which substitution to make, okay? So here, this should feel like it's kind of coming out of thin air. We are going to use the fact that sine of theta is x over 3 in this triangle. So sine, right, is your opposite over hypotenuse. And so that means that here I want my hypotenuse to be 3, my opposite side to be x, and then if you do the Pythagorean theorem and solve for the other side, you will get the square root of 9 minus x squared, okay? So notice this thing is appearing in my triangle. That is no accident. That is actually exactly how I'm deciding to make this triangle. And then the other benefit here is that sine of theta being x over 3 means it's really easy to solve for x. In particular, x is just 3 sine of theta. Now, that means I can solve for this part, right? I can just plug in for x. My other thing that I need to use, need to get rid of and put in terms of theta would be dx. And so here my dx would be 3 cosine theta d theta. And so when I rewrite this, I have x, which is 3 sine theta. So this is going to be integral square root of 9 minus my 3 sine theta, the quantity squared. And then my dx is 3 cosine theta d theta. And so I'm literally going to replace that whole dx with 3 cosine theta d theta. Now, your first thought might be, did we just make this easier? Because it definitely doesn't look that way. And that is a valid thing to think. But let's do a little bit of gathering of terms and simplification and see if we can make this a little nicer, okay? So the first thing we're going to do is, I guess, I'm going to pull out this 3. Just pull it out to the outside. And I'm going to simplify this inside by just, squaring 3 sine theta. So this is 9 sine squared theta, cosine theta d theta. And this inside, I can pull out a 9. And then that's 1 minus sine squared theta, cosine theta d theta. I don't forget my 3. And the square root of 9 is 3. So I can actually pull that out as a 3. And have square root of 1 minus sine squared theta, cosine theta d theta. And then I have one more thing that I want to do. This 1 minus sine squared theta, the Pythagorean identity, the first thing on our little list of trig identities, says sine squared plus cosine squared is 1. So 1 minus sine squared is cosine squared. And so what I'm really dealing with here is 9, pulling out the other 3, times the square root of cosine squared, cosine d theta. And, well, square root of cosine squared is just cosine, and cosine times cosine is cosine squared. Now this actually looks not as terrible, right? Suddenly it's just like one function, it's something squared, seems not too bad. The problem is that we don't know the integral of cosine squared. We know the integral of cosine. But we also can't do u sub here because I don't see a sine, right? I don't see the du part if u is cosine. And so this is where we want to use another identity. So the half angle formula says that cosine squared is 1 plus cosine of 2 theta over 2. Or a nicer way to write this here, because we can always pull out constants, would be 1/2 times 1 plus cosine of 2 theta. So I'm going to substitute that in here. So 9 times the integral of 1/2 times 1 plus cosine of 2 theta d theta. And then just pull out the 1/2. So this is 9/2. Integral of 1 plus cosine of 2 theta d theta. This is one you might be able to just eyeball. So the integral of 1 is definitely theta. This part might be a little harder. If so, I'll just do it to the side here. So this is an inside function, and its derivative is just 1/2, or it's a constant. And so I can do u sub here using u as 2 theta, and therefore du is 2 d theta. I only see a d theta, and so 1/2 du is d theta. So I can rewrite this as 1/2 the integral of cosine of u du, and that gives me 1/2 sine of u, or 1/2 sine of 2 theta. So, rewriting over here, 9/2, my antiderivative of 1 is theta, my antiderivative of cosine of 2 theta I just did over to the right, that's 1/2 sine of 2 theta, and then plus c. So let me just gather, and we're almost done. So we have a nice solution here. The only issue is I've got some thetas. I don't really want thetas. Should be in terms of x, because I started in terms of x. So just like u sub, we want to plug back in at the end. The only drawback here is the plugging in part is not quite as easy, because we haven't solved for theta yet, but we did know a couple things. So we knew that sine of theta was x over 3, and we had our triangle, which looked like this. These two pieces will be enough for us, okay? So the first part is the theta. Well, that part's pretty easy. I can just solve for theta by using arcsine. Right, that'll cancel out the left side. I can solve for theta. It's arcsine of x over 3. Now, you might think you can do the same thing with sine of 2 theta. But if you have sine of 2 arcsine of x over 3, this doesn't simplify nicely. Basically, this 2 provides a problem. Sine of arcsine, that cancels. Sine of 2 arcsine, doesn't cancel. So this is a big issue. What we're going to do here is use our double angle formula. So what do? We use the fact that sine of 2 theta is 2 sine of theta cosine theta. Sine of theta I have up above, that's x over 3. And cosine of theta I can get here from adjacent over opposite. And so this is going to be the square root of 9 minus x squared over 3. And that will be how I do this one. So this is 9/4 times 2 sine of theta cosine theta plus c. And then I just rewrite this bad boy as 9/4 times 2 times x over 3 times the square root of 9 minus x squared over 3 plus c. I don't care a ton that you simplify. If you want to here, just note that the 2 3's cancel with the 9, and the 2 cancels with the 4 and leaves a 2 on the bottom. And so you would just have 9/2 arcsine of x over 3 plus x square root of 9 minus x squared over 2 plus c. And that would be your final answer in terms of x. It's a doozy. It's a decent amount of work to get here, obviously. Trig sub is probably the hardest integration technique. But as long as you know which thing to use and can draw that triangle, the rest is just going to be some trig identities and integration, okay? So now let's try to actually show where that x equals 3 sine theta came from, or sine of theta is x over 3, because that kind of came out of nowhere. So what should tell us to use trig sub? And then when we use it, what substitution should we make? So these are the three situations. So this is number 1, number 2, and number 3. If you see things that look like this and they show up in your integral, then it's probably a trig sub integral, okay? And then for what substitution to make, well, the first one is the one that we saw previously. So when we saw like square root of 9 minus x squared, that was using a equals 3 here. You're looking for some number squared minus x squared in there. And so all of this is depending on the Pythagorean theorem. So we're thinking this type of formula. The only way to get the minus to appear is if you subtract one of these two guys over to the other side, okay? So if you did like b would be the square root of c squared minus a squared. That would be solving for one of the sides that's not the hypotenuse, okay? And so in this case, the easiest way to do it is to have this side be the square root of 9 minus x squared. And then the other sides are, well, the hypotenuse is related to our c. So this should be related to the hypotenuse. So that means this should be a. And that means my other side has to be x. And so that means that sine of theta is x over a, or equivalently, that, x is equal to a sine theta. And so that is the trig sub for this one. And then dx, of course, would be a cosine theta d theta. For the next one, and we're actually going to use this on the next example, the only way that you're getting a plus here is if we're solving for c, because solving for a or b requires subtracting to another side. So here we're looking at the hypotenuse is equal to the square root of the other two sides added together and squared. So that means this has to be my hypotenuse. And then my other two sides are x and a. And the easiest thing to do would be tangent instead of cotangent. So that would be opposite over adjacent as x over a. We like to have x over a instead of a over x because then we can solve for x by just multiplying by a. So x is a tangent theta. That would be the one we use here. And then dx would be a secant squared theta, d theta. And then the last example is similar to the first one, right? We're going to have a minus here again. And so we're thinking that one of the two sides is the square root thing. And this part tells us the hypotenuse, right? That's the only thing that you subtract from. So x has to be my hypotenuse. And then it's just a matter of like, what function do you want to use? Well, it's either going to be secant or cosecant because we want the hypotenuse on the numerator, so it's easy to solve for x. And typically we use secant of theta is x over a. And so that would be our hypotenuse over adjacent. And so that means that my hypotenuse is x. I already have that. My adjacent is a, and that makes this the square root of x squared minus a squared. And so in this case, right, if we solve for x, we again multiply by a, we get a secant theta. That is our trig sub here. And then our dx is a secant theta tan theta, derivative of secant theta, d theta. So these are the three situations. Again, all of these are coming from the Pythagorean theorem, all three of these. These are just going to be a side of the triangle from the Pythagorean theorem. And then just remember that like the thing you subtract from, the x in the last one, the a in the first one, those have to be the hypotenuse. The only way that you're getting a sum here is if that is the hypotenuse already. And so you can kind of fill out your triangle based on that and know what trig sub to use. Okay. Alrighty, so this is going to be our last little example, and then I'll give you a couple exercises. So with this one, again, we should always think, like, can we do something else? So, I mean, two things are being multiplied, but they're also in the denominator, and, like, while x squared is easy to take the derivative of and reduce by my power, this part seems really hard to take the antiderivative of, right? That should kind of require trig sub on its own. So I don't want to do integration by parts. U sub, I mean, you might think like x squared plus 1 is an inside function, but then I don't have an x from like the derivative, which is 2x. So I can't do u sub. And this is not a rational function due to the square root, so I can't use partial fractions. So nothing else works. And importantly, I see this piece. So this is of the form like x squared plus a squared, where a is specifically 1. And so this should make me think trig sub. And specifically, it should make me think trig sub where I'm using the tangent theta 1. So I should have my triangle. This part will be my hypotenuse because that's the only way that I can get a square root of something added to something else. And then the easiest way is to do tangent is x over a. And so in this case, a is 1. So let me just make that 1. And so x is literally just tangent theta. And that means that dx is secant squared theta d theta. Whoops. There we go. So going to rewrite. All right, so my dx is secant squared theta d theta. And then my x squared is tangent squared. And I've got my square root of tangent squared theta plus 1. All right, so that's a doozy. But we got some trig identities we can use here. This piece in here, from the Pythagorean identity, this simplifies to just secant squared on the inside. So tangent squared plus 1 is secant squared. And so I'm going to rewrite that. So I got secant squared theta d theta, got tangent squared, and then the square root of secant squared. But the square root of secant squared is just secant. And so I'm going to be able to cancel one of my secants. So this cancels, my 2 cancels, and this is what I'm left with. Now here, I don't have a lot of options. I mean, I could use tangent squared as like secant squared minus 1, but I can't split denominators, so it's not super useful to do that. On the other hand, if I want to simplify, something I can do is to just turn things into sines and cosines and see like what cancels and what doesn't. So here we're going to use the fact that secant theta is 1 over cosine and tan theta is sine over cosine. So this rewrites as the integral of 1 over cosine theta divided by sine squared theta over cosine squared theta, because it's squared, d theta. If I divide by a fraction, it's like multiplying by the reciprocal, which is way easier for me to handle. So this is cosine squared over sine squared. And now I can cancel a cosine, and I'm left with cosine theta over sine squared theta d theta. This here is actually doable, okay? So from this step, you should note that we've got a secret inside function here, right? Like if it helps, you could rewrite this as cosine theta, or I guess for me ordering it, I'm just going to write this as sine of theta to the -2 power, and then cosine theta d theta. So I've got that inside function there. I'm going to use u sub and use u as sine theta. So my du is cosine theta d theta. That means u is sine, that's this part, so that's u to the -2. du is cosine theta d theta. That's exactly this part. So this is just du. And I can just use reverse power rule. I raise my power by 1. That's going to be u to the minus 1. I divide by that power, negative 1, plus c. And so I get, substituting in for u, negative, because dividing by negative 1 just makes it negative, sine of theta to the minus 1 plus c, or alternatively just negative 1 over sine theta plus c. So your first exercise out of the two is rewrite this, because I have theta right now, and I want my final answer to be in terms of x. So I want you to rewrite this from here in terms of x. So, whether that's solving for theta, using your triangle, this is what I want you to do. And now for your second exercise, this is going to be not too dissimilar from the last one, because there's another square root of x squared plus 1, but I want you to try to do it all the way through. So I want you to use trigonometric substitution, make the right substitution, and work this one all the way out and get your final answer in terms of x. Okay? Thank you for watching.